Okay, so last time what we were doing was we were trying to model how thermometers work. And the reason why we were doing this is because it explains our understanding of what happens to the behavior of particles. Okay? And mainly we're trying to focus on being able to model how particles behave at different temperatures. So we had this um, thermometer model we did particles closer together. If it's a liquid, we made shorter arrows on it to show that the particles are moving slower. And then if we increase the temperature, the level of the fluid went up the tube of the thermometer, giving us a higher temperature reading. We were trying to explain why that would be the case in terms of particles. And so if the particles are moving faster, what's going to happen is they're going to collide with one another with more force. It's going to cause them to spread out more. And we did the bigger arrows to show that they were moving faster. So on your quiz, I was kind of disappointed. I told you guys exactly what was on your quiz, exactly, and still had people getting like 3 out of 10, 4 out of 10. We don't do descriptions and words on models at all. I'm trying to think, why is it that I can tell my students exactly what they need to be able to show me, but they still don't know as I look around the room and see people on their cell phones? I would say that that is probably the reason. So need to get that fixed. If you missed points on the other questions besides the modeling, I was looking for two things. I was looking for you to tell me that with an increase of temperature, the particles will spread out. So spreading out more is one part and move faster is the second part. Okay, in terms of the diffusion of the air freshener through the room, if the temperature of the room was much colder, then the particles are not going to be moving as quickly. It's not going to be moving the air freshener around the room as fast. Could be a chance that it doesn't travel as far even. If you think about the dye demos we did, then it would make sense if you picture instead of green dye that was air freshener, and instead of water it was air, same kind of process, right? So talking about temperature and its relation to particle motion is what we're focusing on today. So we're going to add a little bit to our notes, and something that we should have learned from the videos we watch, we heard them talking about the Celsius scale. Okay, so the first thing I want to talk about is kinetic molecular theory. Okay? And first of all, understand that the word kinetic refers to moving. Okay? Kinetic means moving. So kinetic energy, for example, is moving energy. All right? And so there's a few basic parts of the kinetic molecular theory, but I want to focus on a couple of them, okay? First of all, we can understand that all particles are in constant, so all the time, random motion. Okay, so we've been working on this. This is what we were supposed to be modeling with our last quiz. So in a solid, for example, they're just kind of jiggling back and forth. So we put all the dots like close together, maybe in rows and columns too. Something like that. So some people were able to do that. Now, the particles themselves do not actually Okay, so we show that these are in motion by just putting little quotes around them. So we learned about doing arrows, call these motion lines. Talked about doing arrows, but that's only if the particles are actually changing position. Okay, so that would be solid. Yeah, a lot of people forgot that. Again, even though I said this is exactly what you guys need to do. All right, so in a liquid, now I'm going to do the same 6 dots, but I'm going to spread them out a little bit. Maybe something like this. And now I am going to put little arrows on them. So this will be a liquid. And just drawing little arrows in random directions. Doesn't matter what direction. Something like that. All right. And in a gas, they're really going to be spread out. And we're going to use the longer arrows. Okay, so that's one idea. And now the speed of these particles, which the longer arrows show that those particles are moving fast, right? Well, the speed of the particles is directly related to temperature, which is the second thing on kinetic molecular theory that I want you to understand. So the speed of the particles and the average kinetic energy are directly related to temperature. So first of all, we understand that all the particles are in motion. And not only that, basically the faster they're going, the higher the temperature. So I said the speed of the particles and the average kinetic energy. So again, this average kinetic energy is the energy of motion. So the more kinetic energy they have, the faster they're going to be going. The less kinetic energy they have, the slower they're going. That's what that means. Does that make sense to everybody? Everybody get that? Are you guys trying to lock in and focus and get this? Understand this? I won't be too long here. So that's the second thing I want you to understand. Now, just a couple more things I want to talk about real quick is because these particles spread out, and we talked about the thermometer, there was this guy, Celsius, that did a lot of studies with the expansion of liquids, and he used mercury because it expanded quite a bit with different temperatures. Okay, so I just wanted to make sure that you guys understand from the video that we saw that the Celsius scale, sometimes you see it as centigrade, is based on the properties of water. So what he did was he took that thermometer, that really crude thermometer that he was working with. Actually, it was another guy working with his concepts that did it. But they decided to make some kind of standard areas for thermometers so that they could make them all the same. All right, so what they did was they made 0 degrees Celsius the freezing point of H2O, water. And they made 100 degrees Celsius is the point, that's where they marked it where water boils. So that's why it's based on the properties of water. Okay, but there's another scale. And it's called the Kelvin scale. And instead of being based on the properties of water, it still goes along with the Celsius scale directly, but they wanted to relate it to energy because the average kinetic energy is directly related to temperature, right? So they wanted to make a scale where the lowest possible temperature would mean the lowest possible energy. What is the lowest possible energy of, or if something has the lowest possible kinetic energy, and kinetic energy means moving of particles, what's the lowest you could possibly get in terms of motion? So slow, 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 slow that there's just no motion, right, Jade? Thank you. Okay, so this scale is made to represent the lowest possible temperature, which they call 0 Kelvin. Now, they don't say degrees Kelvin, by the way, just so you know. It's one of those little things where if you're talking to a scientist and you said degrees Kelvin, they might think you're not really that well studied on this stuff. It's just 0 Kelvin. We don't use degrees. But 0 Kelvin would be the lowest possible temperature. Okay? So this is theoretically no motion. So the particles stopped. And we haven't really reached this yet, but we've come extremely, extremely close. It's just it's hard to measure particles and their motion all the way down to no motion and at the same time not manipulate them and make them move. So it's really hard to get them down to that very, very low temperature. Okay? They call this, by the way, absolute zero. Okay? Lowest possible temperature you can get. Now, in terms of understanding this with regular everyday temperatures, we can relate it to the to the Celsius scale. Now, we don't really use Celsius except in science. In our everyday, we use Fahrenheit here in the United States. We could go over conversions between Celsius and Fahrenheit, but I'm not going to have you do that. But you should be able to convert between Celsius and Kelvin. And it's really easy to do. This lowest possible temperature, 0 Kelvin, is equal to, they found this out in Celsius, negative 273.15 degrees Celsius. So all we have to do to convert between the two is take the Celsius temperature and add 273.15, and that will equal the Kelvin temperature. Makes sense, right? So if the lowest possible temperature is negative 273.15 degrees Celsius, if we wanted to convert that to Kelvin, we would add 273.15, which would make our answer 0, which would be 0 Kelvin. Does that make sense? And that's where I'm going to stop the notes for today.